All right. So last time we talked about graphs and we talked about traveling salesman problem and kind of the um, almost a time complexity issue as it relates to the traveling salesman problem. We walked through a pretty simple example of it and saw that it's the way to calculate shortest path is pretty verbose, right? I mean, we had to go through quite a bit of stuff. So you can imagine as soon as the number of cities and the number of roads, all those things starts getting larger, it starts getting significantly more verbose, and then you start dealing with running out of memory and that kind of stuff. So it's actually quite an interesting problem to look at. We won't be able to fully look at the traveling salesman problem. I do think that Dr. Locklear looks at it in 490, so you will see it in a little bit more detail in there, but we'll at least look at the underlying data structure here with the our graph. But it's sufficient for us to say that traveling salesman problem is a problem from a time complexity issue, right? It's and then it kind of amazes us how some of these GPS applications work in real time. How do you suspect if you were writing these GPS applications? Assuming that under the hood they're doing something along the lines of the traveling salesman implementation, Dijkstra's algorithm, maybe with some sort of optimization, just make some assumption there. But how do you think they are able to, I mean, you're not going to wait 20 minutes for it to plot your route from here to Chicago, right? That's not going to be something we're going to do. And, so how does it do it? If you were implementing this, so you're the developer working over at Google or Apple, whoever, the various, or TomTom and Garmin, whatever. What would be some of your approaches to make the GPS lookup faster? Yeah, so I mean, roads aren't just moving left and right, correct? So chances are, even though these things take a long time to do, I mean, it is not an infinite amount of time. It is a finite calculation. And maybe they go back through and they check what's changed, whether, I mean, you've probably run into this before with GPS, where it takes you one way and there's actually construction there and it didn't know about it yet. You kind of missed the window of update, right? Like roads closed and Google wants you to go down that road.
I would think that the roads that people travel the most are probably the ones that they need to run those checks on the most often as well.
Yeah, so now we start looking at various real-time optimizations because there's layers to something like Google Maps, right? As you're looking at it, so interstates probably are going to be we're most concerned about traffic jams and stuff like that on interstates. That isn't to say that other roads maybe don't update as well, but maybe there's a fairly consistent ping rate, for instance, here maybe on 43. Down in Chicago, the Loop 294, 94 through the heart, maybe 57 as it's still in the Chicago area. Once it gets down into downstate Illinois, nobody cares. So as soon as you leave a South Chicago zip code, the fact that you have maps, you should be grateful. There's it's Democrat versus Republican. I think it's a it's a thing. Oh, you found it? Thank you. So I don't lose it. Thanks. All right. So in any case, we can make all sorts of decisions about how often do we check, get updated traffic conditions. So that's another data feed, right? The current traffic conditions. Chances are 294 isn't going to spontaneously move. And although sometimes, like when they do construction, the road does, they start sharing. You got, especially in the big cities where you got 4 or 6 lanes sometimes in different directions, they can turn. Like, oh, we'll just have 3 go this way, 3 go that way. Where it gets really entertaining is the the cities like a Chicago where they have the express lanes that are closed sometimes. So during different times of the day, they go in different directions. You've seen those lanes? Those are. I always wondered what would. Yeah, they do. What if you were in the transition? I mean, it is an interesting thing. Like, how do they have what they have to do is they have to close one end and then let the other end empty. But is there just like some guy that stands out there and says, "This is no more cars," or is there like a little clicker, like an auto clicker on either end that as the cars are flying by, it's like, okay, we got 17, 18, 19, close the gate. 18, 17, 16. Thank you.
There no parking.
No parking.
Yeah, it's in the front and on the back. On the back, they have a event on fitness center or something.
See, we have your full complaint in 360-degree video.
All right. I'll complain. That's cool.
It is interesting what changes between week 1 and 2 and week 14 at the school. Because week 1 and 2, everybody complains about parking. It's not like we have less students or less employees. But then all of a sudden, what happens? Do people kind of settle into like the spots they go for? Is that like a human pattern?
People start skipping class.
People drop out.
But is it enough to make it go from, like, oh my gosh, parking is this huge issue to now there's not? I mean, there really isn't.
I wouldn't think there would be enough. I think you're right that it's just the people eventually settle.
Usually the first week too, they like allow residents like to park on in the lots like normal, and then they'll be like, oh, by this date
You have to be in the garage. Okay, I gotcha.
So then
That's a good point.
I think plus you. Well, never mind.
You know what the best solution is for, because a lot of times it's the employees also complaining, right? You know what the best solution is? Get to campus early. I get right next to the door at 7 in the morning. Just right there.
What bothers me is the one car in the parking structure that campus safety won't do anything about. It's been there for like 2 years.
Really?
one that has all the dust on it.
Yeah. I've been in there 4 times to talk to them about it. And I've been like, I agreed to campus safety regulations. It's in your text. It's on your website. This is what it says. You can't have more than one car on campus. If your car is considered abandoned, then it gets towed. If it can't run, can't move.
Well, now you have a built-in excuse. Any ticket or anything they give you, you say, look, you're enforcing this rule, but not that one?
I tried that.
Wait,
That doesn't work either. They'll want you to pay your ticket.
Does it have a legitimate parking pass on it?
It's got a teacher's parking pass on it. It's a professor that basically just didn't.
They use it for they use it for storage.
Yep.
I should do that with my boat.
The car is literally
People
not.
literally drew pictures on it, like out of the dust.
They've been drawing like really offensive stuff on it.
Yeah.
At one point there was a Nazi swastika on it.
Well, now I'm like thinking, I mean, I would be like a decent place to put my boat during the winter.
It's on the first level too.
I mean, if they're not towing anybody,
It's prime real estate.
maybe I should put my boat right in the entrance.
Just block one of the doorways to the staircases on the side.
You honestly probably could put your boat on the first floor with where all the handicap spaces are that nobody uses.
Park it in the handicap spaces, but sideways. Don't you hate that?
It's big enough to just leave it.
You can park it on the far end on the third level.
Nobody parks on the third level?
Not on the far end.
Huh.
There's like 2 cars that are parked.
That's the longest walk.
And I don't know why.
Again, we're seeing human nature play into this argument. All right, so something she pointed out with the GPS stuff is they can do a whole bunch of pre-processing because a lot of this stuff isn't changing constantly, right? So Google can put their all their horsepower at this for a week or something like that, and just basically build up a giant database of possible connections, right? And I mean, I don't know if it's possible or not, but I mean, I assume that. Well, I don't know. I mean, Google. It occurs to me that Google effectively advertises, operates as if they have unlimited storage. I mean, because I've just been uploading 2 and 3 gigabyte videos on a daily basis to Google for years, and it's like a non-issue. And I'm sure they do some sort of compression stuff and it turns into a smaller file size, but it's not nothing. So maybe they do just literally map every road for every town, for every street in the entire world, and they just have it stored in a giant database. I wonder how much data that is. I mean,
cars that drive through and take pictures of every.
Well, that's for Street View.
Yeah, but
yeah, they don't. They definitely don't have 100% covered in Street View.
Yeah, I'm sure, but
that would be interesting.
They're probably mapping it too when they do that.
But actually, what when they will start having significantly more coverage on Street View or higher resolution stuff at that level, is I know they're working on technologies with network drones. So now think about it from so this kind of becomes a a technology argument and how technologies can complement each other. So we already have these drones, right? We already have the ability to control a drone. Well, what if we can programmatically treat drones almost like recursively? Okay, you go here, you go here, you go here, and there's a whole programming route, GPS, where they just go out and they do their thing. They come back and download their video. So, you get enough drones, Google just sends out a fleet, and they basically just map, a city. You're sitting there and you think it's almost like a biblical like locust storm type thing, but no, it's drones. Wouldn't that be awesome? Yeah. Right. That's actually going to be very interesting moving forward. You're going to have all sorts of drone traffic, and they're going to have to, it's like a lower layer of like air traffic control. But then you're going to have the airports clear. That way, like a 747 to just mow through a bunch of drones.
There are regulations about how close drones can fly to an airport.
Right, but the regulations right now are for humans. To there's rules for like if I'm going to go and drive a drone, but so you're relatively limited by the number of people who are flying drones, which is plenty of people, but not a ridiculous number of people. Well, now if drones become a major part of problem solving, and you have a place like Google that has a fleet of 300,000 drones that are at all times deployed, and they come back to the little charging stations and take back off and zip off, you might have a situation where you might like run into a drone storm. The sun's being blocked out.
They'd have a collection crew for dead drones or something.
That's right. Yeah, just like who. It always interests me in who actually picks up the animal carcasses on the interstate. What percentage of those are picked up by like I don't know if it's like animal rescue or something like that to dispose of the body, or just like guy who wants dinner. Gets out, pokes around, decides exactly how fresh this kill was, and you see him loading it into the trunk of his Civic or something.
Isn't the DNR partly responsible?
Probably, yeah. I don't know.
I've seen a guy do that in Wyoming. He hit a deer.
Yeah,
Just put it in the back of his truck.
Yeah, if I got a dent in my truck, I'm gonna get dinner out of this.
I see a guy when I go to fishing on the up north. He literally just eat the deer, and the deer just lay on the ground. He just pick it up, the deer, throw it.
Oh, I thought you were indicating that he eats it. Like, gets out of car with like he has like a travel fork and knife, and just kind of plops down on the shoulder and just starts feeding. Well, I mean, you have like some fishermen that they bring the little grill out or whatever. They'll cook their fish right there. I mean, there's travel grills. I mean, I guess you could grill up some deer. Yeah. See, we joke about it here, but there's parts of the world that they would kill for a somewhat spoiled deer carcass. It's probably fine. Plus, I think lions really have like a pretty broad range of what's too spoiled for them. They'll just keep eating. So when you're in Wisconsin, you see a dead deer, be on the lookout for lions. Where was that? Was it last year? There was some town. I don't remember where it was. It here where there was a lion?
Yeah.
Was it around here?
Yeah, around here, around in McLean.
Right. Yeah. So I mean, they were talking about it being like a, you know, some sort of hybrid cat or something. I mean, I saw a picture of that thing. I think it looked like a, you know, like a savannah lion. You know, like keep your children inside type thing. And you should stay inside, not just your kids. Everybody stay inside. All right, so we got on to lions eating people. So let's how do we transition this back? But so, anyways, one kind of problem-solving approach to any sort of big data type problem involves pre-calculations, right? Because we can retrieve data oftentimes quicker than we can calculate. Well, oftentimes is probably the wrong phrase. Sometimes faster than we can calculate data in time complexity problems like TSP. Right, so we'd rather just have the data available. Okay, so we talked about our graph implementation where we're going to have kind of two different objects. We're going to have a vertex, which is going to be a collection of edges. And what's an edge? An edge is a destination vertex, so it's going to hold a couple of different pieces of information. It's going to say, where does this edge lead, and what value is associated with this edge. Right, so our data structure for that is relatively simple. So let's go in here and let's just create a new project for this guy. Start new Android Studio project. Graph simulator. Have I been putting these on the desktop? Oh, whatever, I'm going to put it up on GitHub anyways. Okay, we'll just assume that's all good. And I do empty activity, right? Well, is that the default by default now, or is it remember my default? Oh, that's unfortunate. All right, so we'll just get the Android project, but we're mostly going to be building our own Java objects here for the immediate future. All right, so I'll go into our package here, and I'm going to do a new Java class. It's very sad. You can't click sad. Does it have to finish processing? New. Aha. All right, so we're going to call our first one probably a vertex first, because we're going to implement the edge in terms of vertices. So we're going to have a vertex class. All right, we go back here. We see a vertex is going to have a collection of edges. Let's go ahead and create our edge class at the kind of alongside this guy, so we have access to both of them. All right, so there's our edge class. So go back to vertex, and we're going to decide that this guy is going to be a collection of edges. So how many edges will an individual vertex have? Any amount, 0 or more. What kind of data structure allows us to hold kind of a flexible amount of things? Who? Array list will do it. Linked list, array list, and linked list are kind of the same thing. I think there are some performance differences between them, but for this course, we've thought about linked lists, right? So let's we'll go ahead. We've used the built-in linked list, the Java built-in one. I believe so, right? We have it. We did once, okay, well, whatever. So it's in java.util, we're gonna use it right now. So if we didn't, you're gonna see it right now. So we'll use the built-in one. So this thing's called generics. I've talked about that. Yeah, I've talked about generics. Okay, so probably in terms of this. So we're gonna create a linked list specifically of edges. All right, so I'm gonna have a linked list that holds edges, and here it wants me to, what is that, option enter on this? Nailed it. So linked list of edges, let's call it the edges. And we'll just keep it generic there, and then we'll actually give it its value in the constructor. You don't have to do it that way, but that kind of reinforces the idea of a constructor initializing stuff. It also guarantees that we don't use up memory until we actually instantiate, although it'll happen that way anyway, so it doesn't really help. So to create a vertex, the very least, we're going to say the edges is equal to a new linked list capable of holding edge objects. Okay, so that's what a vertex will look like initially. Let's go back to our paint by number here. All right, so now let's go into an edge. An edge has a destination vertex, so it's going to hold one piece of information where this edge leads, and then a second piece of information, probably an int for the weight. All right, so we'll go over to edge. All right, and we'll make that other variable here. I'll go back and make it private here real quick. So we're going to make our the edges a private variable inside of vertex. We'll go to edge. We're going to say private vertex destination. And then we'll say private int weight, something like that. And then when we build an edge, we're probably going to build it with a destination and a weight in mind. So go ahead and give it a constructor that takes both of those pieces of information. So public edge is going to take in a vertex destination and an int weight. This dot destination is equal to destination. This dot weight is equal to weight. All right, so that's an edge. All right, and we probably kind of think ahead here. Well, I don't know. I don't like doing that. I don't like thinking ahead. Stay in the now. We're probably going to need some getters for these guys, but I kind of like to let the code organically grow. So when I need a getter, I'll add a getter. That's more just what I do. Yeah, I think it's probably safe to go ahead and create getters now if we wanted to. All right, so a vertex has a collection of edges. Initially, it initializes that collection of edges to being an empty collection, an actual collection of edges. Up here, this guy is a variable named the edges that will be capable of holding a linked list of edges. But I haven't actually given it a value until I initialized it here in the constructor. Okay, so we've done this collection of edges thing. So for our graph, so we're going to need a graph data structure now. So a graph class, and that guy's going to have a vertex, okay, with a root. Let's go ahead and create our new Java class graph. All right, we'll say public vertex. We'll just call it root. It's not typically. I don't know. I don't even know what did the book talk about like a formal starting point name for a graph? It's pretty commonly graphs allow you to start at any of the vertices. So for our tiny version here, we'll just call it root and just move on with life. All right, so we're going to have a root vertex. We should have the ability to add a vertex to our graph. Okay, so what does adding a vertex to a graph mean? What is a graph? We talked about vertices or vertexes being a collection of edges. A graph would be a collection of vertexes or vertices. I like vertexes better, even though I don't think it's grammatically correct. It's correct in terms of Java objects. Yeah. With one of them, we've let stand out as being our entry point, right? How do you get into the graph type thing? Okay. So that means we're going to have a linked list of vertices for, or linked list of vertexes. So we'll say, and I don't know why I made that guy public, make it private. So I'm going to make private linked list of type vertex, and we'll call this guy, did I spell it right? Looks pretty good. We'll call that vertices, because vertexes might look funny. So now we're going the other direction for a whole different reason. All right, so now we'll do public graph And we'll say this dot root is equal to null. This dot vertices is equal to a new linked list of vertex. All right. So that is our initial graph. That's the empty graph, right? Okay. So let's go back in here. So we need to have the ability to add a vertex. And if it's our very first vertex, we'll go ahead and set it as the root node. I think that's a fair enough assumption. So we'll say public void add vertex. What do we need for a vertex to exist? A vertex doesn't need to have any name or anything like that, so we don't need to take any information for that. So we'll add a vertex. So we're going to say vertex, the new vertex is equal to new vertex. All right, so that's our new object we're going to add. Then we'll ask the question, if this dot root is equal to null, then this is actually going to be our top level vertex. So we'll say this dot root is equal to the new vertex. Regardless, we want to add this vertex to our list of vertices, right? So this dot vertices dot add the new vertex. So now we've added that guy. All right, so now we'd like to be able to, let's make sure we have the ability to add edges. So add the ability to add an edge between two vertices. So we need to have the way, a way of creating a edge. So I can go ahead and I can add a whole bunch of vertices. So last time we kind of drew a picture, right? Did I have a good picture? Sort of. No, that's not from last time. Oh, whatever, that's our rotations. So I can go ahead and, we had our map last time of Grafton to Mequon to Glendale to Germantown. Who was Glendale? Glendale's gone. Poof! Google Maps better run its update. The whole town's gone. Good luck getting to Bayshore. All right, so we can go ahead and add those vertexes, right? But now we want to create connections between those vertexes. So maybe a connection from me to you, connection from me to you. Then there was a connection from you to Glendale, you to Glendale, and we had the two of you connected too, right? Okay, so now with our graph, we have to think about how do we want this data structure to allow us to create these connections. So we're creating all our vertices initially, but we don't necessarily have a clean way of referencing our various vertexes to say I want to create a link from you to you. You're the destination, and that link has this value. Does that make sense? So we need to have that ability. So we're going to need to be able to show our list of vertexes, okay? And then we need to be able to select a vertex somehow, and then choose the destination vertex and give it a weight, okay? So we can provide an Android interface for this. Might be a little short on time to do it. Shouldn't be horrible. Just be a list of strings. Guess we could just do it because that'll be a good example. Have we done array adapters in here? Like show a list of stuff? All right, so let's just do that quickly. We'll do a simple one. I'm going to give myself a reference real quick, but I'm pretty sure because we're going to use the simple one that just holds strings, so we don't need to create our own default of, yeah, so we're going to use the string one. So, so you've seen this on other mobile applications, right? Where you have, just kind of the scroll view thing that has a bunch of rows in it. So built into Android, it comes with kind of like a simple row. Same thing with iOS. It comes with a bunch of simple rows. Now, if you want your rows in your table view to be a little more custom, you would then have to create your own layout for that row item. All right, but we're going to keep this simple. So we're going to create an array adapter of type string. So that means that this guy items here is actually going to be a list of strings. So what we're going to do then as part of this is let's go ahead and let's name our vertexes. All right, so we indicated last time we were kind of building cities. All right, so we'll name our vertexes. So we're going to teach a vertex how to also store a name. So this guy will take in a string name as a parameter, and we'll say this dot name is equal to name. All right, then when we add a vertex to our graph, we're going to go ahead and give that guy a name. So this guy's going to take in a string name for the name of the vertex we're adding. We'll go ahead and pass that name into the vertex that we're adding. Now I'm going to keep track of a second list here. Okay. Now this guy, items, they probably defined it somewhere up here, is going to be a array list of strings. Okay, so that's the kind of animal that guy will be. So I'm going to go ahead and say private array list of string objects. And let's call this guy Vertex Names. So even though those names are housed within our vertex objects inside of vertices, because we're using the simple list approach to this, we're going to go ahead and keep a separate array list of just the names, so we have an easy way of showing them. All right, but we know that these two things are effectively a parallel array implementation. Bucket 0, the name of bucket 0 in my array list is associated with the actual vertex that lives at bucket 0 in my linked list. Make sense? All right, so every single time we add a vertex, not only are we going to create a vertex with that name, we'll also say this dot vertex names dot add, and we'll add that name. We probably also, just for completeness, want to keep track of the root name, even though that will be in our list of names. Actually, you know what? How will we even use that? It'll be the first element in our list anyways. So that's always going to be the root. So with that in mind, we probably didn't even need to keep track of the root, but we will. So let's forget about root name. The root of our graph is always going to be bucket 0 of our linked list called vertices. But we'll treat it as an easy way of grabbing it through the variable called the root. All right, so we went ahead and we added our, I'm going to go ahead and add that down here with this. It doesn't matter, it won't change our logic at all. So if this is the first vertex we're adding, we'll go ahead and set the root to that guy. In any case, we'll add the vertex to our list of vertices, and we'll add the name to our list of vertex names. Okay? So what we want to do here is we want to be able to add a bunch of vertices. So we're going to start off by being able to just put a whole bunch of names in, right? And we want those to fill into our list. So let's go into our main activity here. Let's go ahead and create our See, why are those pictures? Those pictures are wrong, aren't they? That's a picture that shows vertical stuff, right? But it says horizontal.
The lines are horizontal. The line, yeah, the line is even though when it's actually on the screen it displays things.
That is stupid though, right?
Yeah, it all depends on how you think about it. Not very logical.
All right, so we have our vertical linear layout here. So I'm going to go ahead and put in a text box. Oh, that's I want to read something in. That was under widgets. Is that right?
No.
Just plain text. Yeah. All right. So we'll go ahead and add that guy there. Get the properties out here. All right. Well, we're going to call this guy Vertex Name ET. And the hint will be Vertex Name. And it won't have any text in it. All right, and then we'll have a little button in here for add. That's a widget. All right, so there's our button. That's going to be add vertex. All right, and so we want those guys to, when it goes into this, when we click add vertex, it's going to call our add vertex function, right? So that means we need to have our add vertex function get called by another guy, right? Because our function is going to have needs to have a view v or whatever as a parameter in order for it to show up out here. But then ultimately we want it to go into our list of names, and we want that list of names to drive this list view. Now we've kind of built our own list views before by creating text views. So now we're going to actually use a list view. Should be in, is it in layouts?
It might be containers.
That sounds correct. List view. So I'll go ahead and drag a list view out here. All right, so there's my list view. And we're going to give this guy an ID of vertex list view. Okay, that way we have access to it in our code. All right, so notice that this guy kind of looks like it has items and sub-items in it, so it kind of gives you that default scrolly looking view. Okay, so let's go back into our main activity here. Actually, let's go into our we'll go into our main activity. Let's go ahead and give ourselves a public add vertex view v, and this is going to be void, right? All right, so then inside here we also want to keep track of our graph. So we're going to say private graph, the graph, and then inside of on create, let's go ahead and give the graph a value. We'll create a brand new graph, and if you look at our constructor for graph, it takes no parameters. So we'll control a graph. Now we're also going to need our list view in here. So let's go ahead and say private. We'll need our edit text as well. Private edit text vertex et. Private list view is vertex list view. Go connect those couple guys up. So this dot vertex et is equal to the edit text version of this dot find view by id r dot id dot vertex name et. Here I'll name that guy the same thing, Vertex Name ET. Similarly, here, let me hide this for right now. We'll say this dot vertex list view is equal to the list view version of this dot find view by ID r dot ID dot vertex list view. So we'll go ahead and give ourselves access to a couple of those guys. Right. So now we need to go ahead and we need to associate some stuff with that list view. Kind of tell that list view what list of stuff it's going to be showing. All right. So we wanted to show the list of stuff associated with the name list of our graph. All right. So let's go back to our graph and we need to go ahead and expose our vertex names from the graph. So we're going to generate a getter or setter. Actually, I'm just going to write it real quick. So this guy's going to return an array list of string called get vertex names. And this will return this dot vertex names. Okay. So that's what that guy will do. Now we have access to it. So now what we need to do is we need to create our array adapter. And our array adapter, among other things, is created in terms of that array list. So let's just peek back here real quick. So we're going to create an array adapter of type strings for our items for our list. It'll be a brand new array adapter built in terms of this context. So that's going to be our activity. A simple layout item, and then our list of items. So I'm just going to steal that line here real quick. Save us a moment. So I'll go ahead and we need to import that guy. So we're going to create a new array adapter. We'll call it items adapter, whatever. And we're doing it in terms of this. And then here's this, notice this says android.r instead of r dot. So r dot is our stuff. Android.r is stuff built into Android. Okay, so Android has built into it kind of a generic row for a list view. That's what this simple list item one is. There's a two or three of them that are built in there. I think one gives like a subheader and stuff like that. Make sense? But this last part, this is the actual list of items. This should be an array list of strings. So we get our array list of strings from our graph. So we'll say this dot the graph dot get vertex names. Does that make sense? That's where our array list of strings came from, the thing that we want that list view to populate with. All right. So now finally what we need to do is we need, well, finally for right now, just to get stuff to show up, we need to go ahead and let our list view know about our array adapter. So this dot vertex list view dot what is it? So add adapter, set adapter, and the adapter we're setting is called items adapter. Make sense? So we create the adapter, and that adapter handles the job of taking a list of strings and populating this simple list item one with it. If we wanted to make a row be something fancier, where it had images and extra stuff in there and 5 or 6 different labels, then we would need to create our own layout for that row, and which isn't a problem. But then we'd also then need to create our own array adapter subclass to teach it how does it populate that thing with. So that's why we're using the simple one. Will take less time. Okay, so let's go ahead back out here to our main. So we're going to go to add vertex. Actually, hold on, did I finish looking at the code in here real quick in main activity? Okay, so for public add vertex, this what we want to do is we want to call the graph's ability to add a vertex, right? So we're going to say this dot, the graph dot, add vertex, and this guy requires a name. The name is going to be this dot vertex name et dot, what's it, get text dot toString. So that'll grab the text from that edit text, pass it to our add vertex function, and let that guy go ahead and do the magic of adding a vertex. Sound good? All right. Is it actually complaining about something in here?
Semicolon. You forgot a semicolon.
I always forget semicolons. That shouldn't be that big of a deal. Yeah, yeah, yeah.
Vertex Names.
Oh, this guy? No?
Vertex Names.
Ha! Testing you.
I'm passed.
Okay. All he did is notice a little red squiggly. What are the chances I didn't do that on purpose? I told you I'm getting old, people. Let's see if the we still cooking? We're not. Looks like it. So I said it was an hour and 6 minutes was the original.
Something like that.
Yeah, so it looks like it took a 25-minute video before it croaked. I don't know. I mean, it is still live. There, I'll just start the video again. We'll just let it keep cooking. I want to say it's maybe 300 or something like that, which is pretty inexpensive. 360 camera. This is like entry level. So. Well, now we pretty much got to figure it out from a technology perspective. It did not disconnect from the network, so we're good there. It's still powered on. It's at full battery. So all the stuff we had problems with yesterday are fixed. Now the only real problem is maximum record length. And that potentially is a setting that I'll just have to look at, right? But it appears to be 25 minutes right now is our, I mean, that seems like a pretty, you know, it would be very coincidental if it just happened to die at 25 minutes. Seems like that sounds like a default value. All right, so we're going to go ahead and set our add vertex up for the on click for that dude. On click. Add vertex. Okay, so I click on this, it reads from this, it adds to my list adapter, and then it should put something in the list. There is a way to update a list adapter, but they usually update on their own. So let's see what we figure out here. Ruh-roh. Doesn't like something. Oh. That potentially is not me. All right, this one's definitely me. Oh, it shouldn't be null. Okay, so let's Did I instantiate things out of order here? So here's my graph. Let's go into new graph. Ah, yes, we did. We never actually gave our vertex names a value. So we were getting a null pointer exception here on this guy because when a graph is first created, we didn't give that guy a value. So where were you on that one, Van? Tested you again. Failed. Clearly, I didn't introduce this error. Just saying. New array list of string. All right. Now it should be empty initially. Woot. All right, so we'll put in Grafton in here. We'll say add vertex. All right, well, it didn't crash, so I think it probably did get added. So let's trace through this. So we told our graph to add a vertex. Fine. Graph adds a vertex. We add the name of that vertex to our vertex names. So maybe we do need to tell the, I think it's actually the adapter. Here, I'm going to actually define the adapter up top here. And then we'll just give it a value here. That way I have access to the adapter down here, because after I add that vertex, I'm going to call item adapter dot notify dataset changed. Pretty sure that's the right line. That should tell the adapter that there is a new piece of information that we've added to it, and it needs to update the list view. Yep, so there's Grafton. Probably wanted to empty it out. We'll put Mequon in there, add vertex, so there's Mequon. Here, let's just add a whole bunch of them so we can see it scroll. So lots and lots and lots of Mequons. So you see we can scroll through that guy now. Make sense? All right, so now something we want to be able to do here is we want to be able to click on one of these guys and actually have it tell us where we clicked. So we have to add an odd item listener to our list view. So let's go in here and see if we can steal a little code for that guy. Here's that custom array adapter thing I told you about before. If you want to use, like for instance, if you wanted to have a list of vertexes and have it extract the pieces of information, but we're not going to deal with that right now. We did the population. Android list view on item click. So we need to add this to the adapter. All right, so here's our actual list view. So we're going to do a set on item click listener. And I think it'll give us, I think this guy will give us the code for it. This dot vertex list view dot on item, let's see, but we're setting it. Set on item click listener to a new on item click listener. All right, so this tells us, this gives us the actual view that was clicked. It gives us the position that was clicked. So let's just real quick do a system.out.println on it, proving that it's working. Let's print out the position. So this should be row 0, row 1, row 2, that kind of stuff. Okay, so I'm putting onto this list view a click listener, so he's going to listen for us to click on it, right? Click on one of the items. When we click on one of the items, it's going to tell us the parent adapter view, which we're not going to use here. It's going to tell us the view that was clicked. That's going to be one of these simple list item guys, which we're also not going to use in this case. But it'll tell us where we clicked on it. And then I think the ID is the unique identifier of that row, which gets automatically set for us here. So it'll probably be like list item 0, list item 1, list item 2. We really care about position because that's going to map to our couple of arrays, right? So we'll just print out position. We should see things like 0, 1, 2, that kind of stuff. Okay, so we'll add Grafton. We'll just add a bunch of Graftons here. All right, so I'll go ahead and click on the very first Grafton. So there's a 0. So I'll 0 down there. I'll click on the third Grafton. That should be a 2. All right, so we're getting the things that we're meaning to click on, right? Okay, so now that we know what we're clicking on, what would it make sense to do? If we're going to add an edge, we're adding an edge from this vertex, the vertex at bucket 0, to this vertex, the vertex at bucket 2, and then we probably give a value, a weight for that edge. Does that make sense? All right, so a little short on time, so that's the easy part of this, right? We now know exactly, here's my 2 vertex, I can click here, I want to add an edge to this guy that leads to this guy. Make sense? All right, so we'll leave that as an exercise for the reader. Let me quickly push this, and then let's go through and talk about the exam for a few minutes. Share project on GitHub. Graph simulator. Okay, nailed it. So, first of all, the exam is Wednesday or Tuesday morning? Tuesday morning at 10 a.m. Okay, so exam's Tuesday morning, 10 a.m. You'll have an hour and 50 minutes to do it. So it's what, I think it's 10:10 until noon is the official time. The exam will be a pretty similar length to the midterm, so it's going to be designed to be about an hour and 15-minute doable exam. So time pressure should not be a problem. You should have plenty of time to finish the exam. I would expect most of you would be done well before the 2 hours, but you do have the full 2 hours if you like it. Okay, time is yours. It'll be very similar to the types of questions I asked on the midterm. So, you know, somewhere in the ballpark of half the exam is going to be programming stuff, half the exam will be other type questions. There'll probably be a conversion question on there. I like conversion questions. Technically, the exam covers everything we've covered. Well, I say in here, but I guess, you know, technically it could cover anything from 200 to 250 because it all builds on top of it, right? But certainly what I mean by that is, you know, you should know how to use for loops for this exam, right? You know, it's like, well, we haven't learned for loops since the midterm, so that's not going to be on there. I would expect for loops to show up in some of the programming type stuff. Certainly the focus is going to be on the things we've done since the midterm. I didn't have like a breakpoint for the midterm. Midterm was up through what? It was stacks? Okay. So, so that's kind of our transition point. So then we talked about queues, not a big jump from stacks. I certainly might ask you something about queues or make you write something that involves a queue, but queues are pretty simple implementations of linked lists, right? You add to the end, you remove from the front. Okay. You wouldn't have to implement a heap or anything like that, but there could be probably a relatively low priority, but there could be a question about a heap on there. The fact that it's a priority queue, a queue where some elements align, where some elements are more important than others, something like that. The concept of a hash function, a one-way cipher, arbitrary size input, fixed size output. Certainly binary trees, so this would be more of the focus point, I think, on the exam, is these non-linear data structures. So really, the class was divided into two halves, right? We had linear linked data structures, the first part, then we have non-linear linked data structures, the second part. So I would focus more time on binary tree type things. Certainly singleton could be on there, or I might, it might make sense to write one for one of the programming assignments. I probably won't ask you about coupling, but you should all know, coupling is when code is reliant on another part of your code. The concept of an AVL tree probably will be on there in some form, so far as that it's a self-balancing tree and what's the benefit of having a tree in balance from a searching perspective, that kind of stuff. I wouldn't ask you to do any rotations, either by hand or by code. That has most to do with the fact that I don't like them, and I don't want to have to figure out whether you're right. So it just is what it is. AVL trees are just kind of complex. If you work with them all the time, it ends up becoming fairly easy. I remember when I originally was dealing with them years ago that, you eventually kind of get the knack for how AVL rotations work, but it's not overly important. When you need to use them, you'll go and learn about how the rotations work, and then you move on with life. Okay, so understand the idea of a self-balancing tree, the benefits of it being balanced, that kind of stuff, and I think that will be sufficient. Certainly, graphs, as we talked about recently, I wouldn't ask you to write anything related to Dijkstra's algorithm, but maybe understanding the concept of Dijkstra's algorithm, kind of the how it applies to the traveling salesman problem, and it's kind of a verbose type of approach, that kind of stuff. Also, some of the things we've talked about, graphs, certainly going to be on there, but that's really just an extension of trees, right? I mean, they're just trees that happen to have links up to other places. So it would be fair game for me to ask you some programming questions about implementing something with a graph or something like that, because you already have done it. You've done it with binary trees and stuff like that. This is just, one more logic step or something like that. Make sense? All right. In terms of the programming questions, the types of questions I would typically ask are going to be, so you got to consider where you think you should be. Well, it's more important where I think you should be at the end of this course, but try to put a measuring stick to yourself and decide, where are my competencies relative to where they should be for the average student graduate, coming out of CSC300? Okay. If you perceive yourself to be on the weaker side, well, then you're going to expect the programming questions to be difficult on the exam. Okay, so I'm going to ask questions that are targeted at what I think you should be coming out of 300, what competencies you should have coming out of 300. So if you perceive you suck at programming, you might want to brush up on that stuff and practice quite a bit between now and then, so you at least come in and don't embarrass yourself. Right? Be able to write some code that looks competent. I'm not going to grade the questions from the perspective of is it 100% correct or 100% wrong or 100% incorrect. But if you show me complete incompetence, I'm going to show you very few points. Okay? So show me that you have a clue at what you're doing. If you make a little mistake, that's not the end of the world. because it is a time pressure type thing. You're writing code in real time, stuff like that. But don't expect partial credit because you wrote the word int. Okay, something like that. So try to measure yourself on where you stand in terms of what the competencies for the class should be. If you feel that you're a pretty strong programmer in here and you're kind of above the rest of the class in terms of competencies, you'll probably find the programming questions fairly easy. All right, so I'm going to try to hit that. Where should you have your competencies coming out of this course? Make sense? Questions, comments, concerns, bribes? All right, I will see everybody at the final on Tuesday.
I can interrupt.